Hello, Science 20s. Our lesson today is on potential and kinetic energy and how they relate to work. I will remind you that energy is defined as the ability to do work. We measure energy in joules, abbreviated capital J. Work, however, is defined as energy transferred by applying a force over a certain distance. So, again, like we looked at when we were in Science 10, if you can apply all the force you want on an object, if there is no distance moved, no work was done. Work is not based on how tired you are. So, you push with all your might on a wall. You could be on the floor exhausted unless that wall actually moved in the direction of the applied force or on a line that's parallel to that applied force, you did not do any work. So this relates to the idea of conservation of energy. Energy cannot be created nor destroyed. It can just be converted from one type of energy to another. So if we think of a ball, right? I have a ball here. I'm holding it a certain distance above the ground, which means it has within this ball a certain stored amount of energy. And we might even call this gravitational stored energy, because if I let go, gravity is going to act on it and push it down. So this is gravitational potential energy, stored energy. Well, the moment I go to throw that ball in the air, when that ball is getting thrown in the air, the moment it's starting to move, all my potential energy is going to go down and my kinetic energy is going to go up. We're transferring energy from one form to another. Remember, kinetic energy is the energy of motion. So while my ball is still going up, 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 now it won't go up forever, right? It eventually is going to slow down and it's going to pause for one brief second, and all that kinetic energy, energy of motion, is going to transfer back into potential energy, stored energy. And then again, it stops for a fraction of a second, and then that potential energy is going to transfer back to kinetic as my ball moves back down again. So we convert energy from one type to another. And this could be lots of different energy. This could be elastic energy, like an elastic band for stored energy. Food has chemical energy that there's energy stored in it. So when you eat a hamburger, you then have that energy in the hamburger to help your body metabolism work. So we have loads and loads of different type. Thermal energy would be type of kinetic energy because, right, thermal energy is the movement of particles. And so all things vibrate or move depending on what state of matter they are in. Well, what I want to do is look at what I would have done in Science 10. I have two pictures here. The picture on the left is kinetic energy. This is a mountain with a giant, we could say it's a giant snowball coming burrowing downhill, right? The amount of energy is here is due to motion. And if I look at this, we can see that it's going to be related to the mass of my snowball as well as the speed of my snowball as I am going downhill. Now, when I go to do this, there's some things I want to point out to remind you of, and that is this is the formula in your data booklet. However, I prefer this formula, mass times speed squared divided by 2, rather than the half. I think this is much easier to move around. I want to remind you that, of course, this is kinetic energy. And so that's going to be measured in joules. This is mass of the object, and so that's going to be measured in kilograms. And then this is speed of the motion, and this is in meters per second. So that is kinetic energy, energy of motion. Something moving, in this case, a snowball rolling downhill, has kinetic energy. In our examples, we're going to ignore things like friction. There's no friction between this mountain and the snowball. There's no air resistance losing anything. The second formula we have is potential energy. Now, we refer to this as stored energy. This is the energy due to the position of an object above the Earth's surface. So in this case, I have this snowball way at the top of the mountain. And I think we can agree that the higher an object, the more energy it has stored. Because if I drop this on your head from this distance, or if I drop this on your head from this distance, the shorter distance is going to have less energy stored up than the higher distance. that's going to land with more energy stored up or transfer more energy to it from gravitational if we let go to kinetic. So in this formula, again, I want to point out some of the basics here. So EP is our potential energy. And it, again, like kinetic energy, is measured in joules. Mass is just what you expect it to be. Mass is measured in kilograms. H, that is going to be our height, and that's going to be measured in meters. And the guy that you recognize, hopefully from a previous chapter, this is going to be acceleration due to gravity, and it's always going to be 9.81 meters per second squared. So what I would like to do is highlight these two formulas in your data booklet, and then let's practice or play around with these concepts and the idea of law of conservation of energy. So how much energy does a car that is 550 kilograms moving at 23 meters per second have? So we have a mass of my car. Oh, I goofed that. I need the correct pen for that. My bad. So we have a mass of the car of 550 kilograms. We have a speed my car is moving is 23 meters per second. We would like to find out how much energy. Now, since the car is moving right away, we know that we are finding kinetic energy. So let's write down the formula. EK equals mv squared over 2. Now, let's check our units. I like kilograms. I like meters per second, so we can now sub in. So I'm going to have 550 kilograms times 23.0 meters per second. And we're going to square that number. And then we're going to take the whole thing and divide it by 2. So in my calculator, 550 times 23 squared, enter, divided by 2, enter, and we got a massive number, 145,475 joules. So lots of energy. But think about it. This is a car. So ideally, if we're picking realistic numbers here, it's realistic that the car would have a lot of moving energy as you're driving down the road. Okay, in this example, we are trying to find the potential energy. So we are locating EP. It tells me I have a book with a mass of 1.50 kilograms. I like that unit. It is sitting on a ledge 6 meters high. I like that. And because we're finding potential, right, the book's sitting on the ledge, so it does have gravity there. And so that is going to be 9.81 meters per second squared. So EP equals mgh 1.50 kilograms. We'll write it again, times 9.81 meters per second squared times 6 meters. So 1.50 times 9.81 times 6.00. I'd like to point out we don't square anything this time. In this formula, this is part of the unit. It's not an actual thing we have to do on our calculator. And so my answer looks like it's approximately 88.3 joules. Okay. So let's look at an example using a car. A car is resting at the top of a hill that is elevated 15 meters. What will be the velocity of the car once it reaches the bottom of the hill? So if I take a look here, I'm going to make a list of variables. So I have a height of 15 meters. We are trying to find velocity. Now, there is a trick to this question, and that is because potential energy is measured in joules and kinetic energy is measured in joules, and since in the law of conservation of energy, energy is neither created nor destroyed, it just changes form, we can actually say that the kinetic energy that my car would have at the bottom of the hill when it's rolling would be equal to the potential energy this same car will have when it's waiting at the top of the hill. So kinetic equals potential. And think about this, joules equals joules. It's going to make sense. So let's write out the full formula. So if this is EK, kinetic energy is the same as saying mv squared over 2 equal EP is mgh. So if I'm trying to solve for velocity, which means I want velocity by itself, I need to get rid of mass over here, which means mass is going to come to the bottom of the other side. Mass on top, mass on bottom, they're going to disappear. So we are going to get rid of the mass. And this is the formula we have sitting in front of us. Again, don't like the 2. So when you cross the equal sign, it can go up. So V squared equals 2GH. The opposite of a square is a square root. So whatever I do to the left, I'm going to do to the right. And so my formula when I'm done is going to be V equals the square root of 2GH. So let's sub this in. 2 times 9.81 meters per second squared. The height is 15 meters. So I'm going to go 2 times 9.81 times 15, enter. And again, I want to remind us, don't forget before you're done, you need to square all this. So I'm going to take the square root of that number. And my number works out to be 17.2 meters per second. What I would like you to do is, I would like you to copy the next slide, follow very similar procedure, and do that one for yourself. Then unpause the video to check your answers. So, a dog on a bike is resting at the top of a hill that is elevated 7 meters. What will be the velocity of the dog once it reaches the bottom of the hill? So again, we're trying to find velocity. So we have our formula. So we have EK at the bottom of the hill is equal to EP at the top of the hill. Again, EK equals MV squared over 2. EP equals MGH. So again, masses are going to cancel out. I am going to be left with V squared over 2 equals GH. So I'm going to move the 2 up, and I'm going to have, after I move the 2 up, I'm also going to square root. So we're going to have the same formula that we had before. If you need to go back and re-watch the start of this video, you can do that. So 2 times 9.81 meters per second squared, and the height is 7 meters. And again, don't forget to square root those 3 numbers. So I'm going to take 2 times 9.81 times 7, square root, my answer, and I'm going to get 11.7 meters per second.